let's talk about how solar cells work. So this is how solar cells work, or this is how it was conceived solar cells work in the first textbook on solar cells written by Harry Hobbs at IBM. You know, many of you have probably taken semiconductor device courses where you learn about drift and diffusion of carriers, recombination of carriers. This is drift and diffusion writ large, okay? And the idea was to sort of model a solar cell the same way you'd model a diode, okay? Makes sense. Solar cell looks like a diode. Why not model it the same way? And these are the equations you get when you do that. You know, but you have things like diffusion constants, diffusion lengths in here. You have generation rate somewhere buried in here. This is the volume generation rate, how many carriers per unit volume the sun creates. And you could solve all these equations on a computer, and you'd get analysis. So the idea was back then that you thought of a solar cell like a diode. You solved the continuity, drift, and diffusion equations. The problem with this approach is, while rigorously correct, it's not obvious how a solar cell works. I mean, it's just buried in these equations. In fact, if you go back to these equations and you set things like the minority carrier lifetime or in there to infinity, the conversion efficiency goes to infinity. So it doesn't even obvious that these things obey the conservation of energy, these equations here. This created a lot of thinking, and it's a fascinating sort of thing that people went through. This just shows some outputs from Harry Hobbs' book, what he thought solar cells, you know, as you vary the junction depths, and, you know, he was getting 16, 17% for the conversion efficiencies, that kind of thing. So this was the state of the art. And but if you step back, really a solar cell works like this. This is a cross-section of a typical solar cell. Light comes in, goes into the semiconductor, and knocks an electron loose, whacks it out of the lattice, okay? That's the little red guy there with the E by it, leaving behind a hole, which is the blue guy. And what you want to do is coax that electron to come out the negative lead, which is on the top here. And you want to coax the hole to come out the positive lead. That's the whole deal. And in fact, it's very simple if you look at it in a different way. So this is sort of to help you look at it in a different way. This shows a similar kind of cycle to what goes on in a solar cell, but this is a hydraulic energy generation where sunlight comes in, heats water, water goes up in the air, makes a cloud, rains, fills up a lake, okay, goes down through a turbine, generates power, goes back into the ocean. So the water is going through a cycle. It's going around in a circle here. And you can map every process in a solar cell into one of these parts of this diagram here in a very one-on-one mapping that's helpful. So this is kind of obvious how this works, right? I mean, everyone understands, you know, this reservoir at high potential energy. Water goes through, spins a turbine, goes back to the ocean at a low potential energy, goes back up and around, generated by sunlight. Kind of clear how that works. The new method that developed in the 80s was to think of a solar cell really in terms of an energy band diagram like this, with one metal contact. This is the p-type contact, and this level here is called the Fermi level. Okay, that's the level at which electrons are full up to in the metal. And that, by the way, from your semiconductor device physics, is the same as the electrochemical potential of that metal. And then as you go into the solar cell, the electrochemical potential of the electron stays the same as you go in like that. There's another, of the holes rather, stay the same. There's another electrode, the negative contact, which is in good connection to the electrons within the cell. And the electrochemical potential of the electrons comes out here. So the electrochemical potential or Fermi level of the electrons and holes are different from each other, and the emphasis in the analysis here is on those Fermi levels. We'll see that where that compares with the lake and the hydraulic in a minute. But the first step then in this whole thing is to knock an electron from a low energy in the valence band right there. So here you see the photon coming in. This is a PowerPoint photon that they found. And it knocks the electron out. gives it the energy of the photon, and it knocks it loose up into the conduction band like this, okay? Immediately after that, the electron loses energy and goes back to the top of the conduction band. It loses energy by emitting phonons at that point, and the hole floats up to the top of the valence band like that, the same way. Now, it's like a bubble, okay? This loss of energy here is analogous in a way to the fact that the cloud was above the lake. The sun brought energy up to the cloud, which was above the lake, and then the rain went down into the lake. We didn't capture that energy of the rain falling until it hit the lake. So this is kind of the loss of excess energy from the light here. And then the idea is, in a solar cell, is to coax the electrons to come out one terminal and the hole to come out the other terminal, okay? The way you do that is you make electric fields in the cell that attract electrons over to the negative collector here and repel electrons at the positive collector. So if an electron went here, it would see this little electric field, little hill. This is very much like the edge of the lake, of the hydraulic reservoir. It's trying to keep the electrons from coming out, right? If the lake didn't have a good barrier around the edge, the water would drain out. Okay. Same thing down here. And when the hole gets to the metal down here, it actually floats up to the Fermi level, like that. Now this is what happens, but it becomes more clear when you complete the cycle. What then happens is the electron goes around through the wire, gives up its energy, goes back and pops into this point here. That does not have to be the same hole that it was left when it was created. Just like when the water got down to the ocean, doesn't have to go at the same spot where it evaporated from, but it completes the cycle. And so, voila, what really goes on in a solar cell, you knock the energy up, collect it, try and get the electron to come out one lead like this, coax it around, and go through. The whole thing in designing a solar cell is to convince the electron to do that and not do something else. And there's a lot of other things it can do. For example, it could, before it even got there, recombine with another hole, okay, like this. So now the electron went up and then it popped right down into a hole. Now if it does that, as I've drawn here, it'll actually emit light. Okay, this is called radiative recombination. If the electrons and holes don't get collected, they recombine. Those are the only two possibilities. They either come out or recombine within the device. This is one type of recombination called radiative. And in fact, this is what a light-emitting diode does. Okay? And solar cells are light-emitting diodes. This shows, in fact, they're fun light-emitting diodes, and this has become a huge method of quality control analysis of solar panels, is to make them into light-emitting diodes. All we've done here is taken the panel and run the current backwards through the panel, and then shot a picture of it. You can do it with an iPhone, believe it or not. These panels glow. They're light-emitting diodes at 1 micron wavelength. Your eye can't see it, but your iPhone can. And you can diagnose immediately all kinds of problems in the panel. For example, you want the cells to glow, so you want them to be white. You can see cells over here on the left that are broken. It'd be very hard to find this without this technique. They're not producing any light. This panel here has had a lot of its solder connections fail. It's brand X, obviously. This panel here has lost a complete string because of the, probably in the junction box, the wiring broke. This is a Sunpower panel. You can see here a line in this thing. That's a crack across the cell, but the cell's still working. So it's curious that these things glow so much. And it's also curious that it took people so long to figure this out because you can't see it. This sort of diagnostic technique is relatively new in the industry, even though the physics are very old and it's obvious that it should work. There's other kinds of recombinations that go on through defects. This recombination in the hydraulic reservoir is sort of like leakage. You know, if the lake had had leakage cracks in it, the water could get back to the ocean without going through the turbine. That's what's going on here. The electrons are getting back into the holes without going through the external circuit. Another thing that they can do is they can go backwards. Remember, we wanted the electron to come out the left side, which is the negative lead. This shows an electron that was unfortunate and went the other way. And it did so by surmounting this little barrier here and getting into the metal and popping down. It's clear just looking at that picture that isn't what you want to happen in it. So this is sort of like water that flowed over the edge of the reservoir through a weak spot or something and back down the mountain. And so obviously one of the design tricks is try and make this barrier as high as you can, make this electric field as steep, as long, and the potential difference as great as you can to keep them from going backwards. That's part of the design of the cell. So anyway, the upshot is that the current is the total generation current minus what recombines. So this idea that you basically focus on generation within the cell and recombination and Fermi levels is the way modern cells are thought of. And it's been that theory of how you do that has been responsible for the vast increase in understanding of how to make more efficient solar cells. This just shows a Sunpower cell cross-section, and where we are able, with cell modeling codes, to tell you everywhere the energy is going within the cell. So of the energy that's generated internally in the cell, 0.2 percentage points is this bulk recombination. 0.2 is occurring here at the surface. This is actually at the surface. 1% is occurring at the percentage point. 0.2 is in the diffusion. All kinds of, every point within the cell, we know what it's recombining. And if you add all those up, it's 4.4%. The thermodynamic efficiency that's possible is 29. So you can see the cell is basically 24.6, which is what a modern Sunpower solar cell runs at. So I hope that gives you some feeling for what goes on in a cell and sort of a feeling for the kinds of design things that need to go on. And I'd certainly be happy to take any questions at this point. Thank you.